center of mass versus center of gravity. Equations above that described for the center of gravity, which was x bar x dw on w x dm on m x rho dv y bar y dw and z bar z dw on w z dm on m and z rho dv are independent of gravitational effects. Since G no longer appears. They therefore define a unique point in the body which is a function solely of the distribution of mass. This point, called the center of mass, is the point of the distribution, solely the point of distribution of this point is clearly coincides with the center of gravity as long as the gravity field is treated as uniform and parallel. If the gravity force gravity field is treated center of mass equals the center of gravity. It is meaningless to speak of the center of gravity of a body which is removed from the gravitational field of the Earth, since no gravitational force would act on it. The body would, however, still have its unique center of mass. We will usually refer henceforth for the center of mass rather than to the center of gravity, also the center of mass has a special significance in calculating the dynamic response of a body to unbalanced forces. This class problem is discussed in Volume 2 Dynamics. In most problems, the calculation of position of the center of mass may be simplified by an intelligent choice of reference axis. In general, the axis should be placed so as to simplify the equation of the boundaries such as possible. The polar coordinate will be helpful for bodies with circular boundaries. Another important clue may be taken from consideration of symmetry whenever. Let me write in the most problem the calculation of the position of the center of the mass may be simplified by an intelligent choice of reference axis. In general, the axis should be placed so as to simplify the equation of the boundaries much as possible. Polar coordinate for example will be useful for bodies with circular boundaries. Whenever there is a line or plane of symmetry in a homogeneous body, a coordinate axis or plane should be chosen to coincide with this line or plane. The center of mass will always lie on such a line or plane, since the moments due to symmetrically located elements will always cancel, and the body may be considered composed of a pair of these elements. Thus, the center of mass G of the homogeneous right circular cone, as this picture, will lie somewhere on the central axis, which is a line of symmetry. The center of mass of the half right circular cone lies on its plane of symmetry. In the picture, for example, here, the symmetry is the center line, the symmetry is a plane, and in this case we have a symmetry plane, and this plane, the line of the center of mass lie on the center of the plane of symmetries. The center of mass of half ring, as shown in this picture, lies in the both states of its plane of symmetry, and therefore is situated on the line AB as shown in the picture. It is easiest to find the location of G by using symmetry when it exists.